Welcome back to Fat Mama Physics. It's been a long time since I've made videos. It's good to be back. I will try to continue to make more videos, but to start us off, I wanted to do some practice with circular motion. Circular motion is one of my favorite topics, and one of the questions that are quite tricky involve gravitation and orbits. So I'm really hoping to go over how to calculate total energy of certain objects in orbit, namely satellites. And this video is two parts. And so the first part is showing more derivations. Second part will be using some of those derivations in some word problems. So here we go. First page here. Here is a worksheet that I have, and I'll go over the first part. First part is a derivation of calculating total energy of a satellite that is in orbit. There's a key difference between a satellite that's in orbit around a more massive planet star versus if something is just placed there in space. So before coming into this video, I expect that you know that the potential energy of an object such as a satellite is given by negative gravitational constant g times the mass of that massive object of the star, the sun, or the planet that your satellite is orbiting, or black hole, times the mass of times the mass, which is the small m here, of your satellite, over r, which is the distance from your satellite to the center of mass, to the point mass of your star or your planet. Okay, so that's the distance r. I also expect that you know that the kinetic energy is given by 1/2 mv squared, where m is the mass of your satellite and v is the speed of your object. Now, in the context of an orbiting satellite, your v would be your orbital speed and r would be your orbital radius. Okay, so now given this, in this first problem, it's trying to it's asking you to find the total energy of anything that is in orbit. We know that, and the total energy, to calculate the total mechanical energy of your satellite is given by the potential energy plus the kinetic energy. So if we write this out, then we are going to get something that looks like this. Total energy is going to be equal to negative big G, big M, small m, over r plus 1/2 mv squared. And it looks nothing like this. The first part looks pretty similar, okay, this part over here, but it's the second part that doesn't quite look similar. It looks like has something to do with 1/2 mv squared. So let's look at the kinetic energy, and maybe that's going to give us some ideas. Now, we know that m is the mass of your satellite. V is your orbital speed of your object. Hey, this is probably a good time for us to review how to get orbital speed. Now, to understand orbits, we have to understand that an object that is in orbit, the force that is keeping it in circular motion is the gravitational force, Fg. Okay, and Fg being the force keeping it in circular motion, which is our centripetal force. This is given by big G, big M, small m over r squared. Looks similar to gravitation, to potential energy. Okay, I expect that you know this one. And also Fc, which is your centripetal force, mass times the centripetal acceleration, v squared over r. Okay, this is, if you know this, great. You might have done this in class. So some of the r's cancel. Here we go, the mass cancel, because we can see how the mass of the satellite does not affect the orbital speed required to be in circular motion at that point. Okay, so then we get v squared is equal to big G, big M over r. Okay, we can leave it like this because the v squared in kinetic energy is already in the square form. You don't even actually have to take the square root, but just for your information or just for your reference, this is it. You may even have this in your formula sheet. But anyhow, the one that I'm going to substitute into kinetic energy is this one over here. Okay, so once we do that, we are going to get E total, which I'll write down here, negative big G, big M, small m over orbital radius, plus 1/2, okay? The mass of your satellite or your orbiting object is still small m, and your V squared is going to be big G, big M over your orbital radius. Looks a little sus, eh? Well, let's rearrange this. We're going to get negative big G, big M, small m over r, okay? Plus 1/2, okay? Now, instead of having this small m there, we're going to make that look exactly like what it is here. So we have big G in front, big M in front. This small one, small m, we'll put in that's the very front relative to here. Anyhow, so then that way we shuffle these variables a little bit, and there we go. We have exactly what the question wanted us to do. All it did was to redefine what that kinetic energy was. Now, when you look at this, you may even see there's even something more suspicious going on here. We have a big G, big M, small m over r here. We also have the same thing in the kinetic energy portion. Wow, how much of a coincidence is that? Okay, and if we just treat this as like a big hunk of metal, I don't know, treat it as a variable, treat it as anything, a block or whatever, okay, then what this is trying to say is that a negative 1 of that, okay, plus a positive 1/2 of that is your total energy. I can even rewrite this and say this is kind of like saying negative 1 plus 1/2, right? Negative 1 plus 1/2. Negative 1 plus 1/2 is a negative 1/2. So I could actually simplify this even more and say this is 1/2, and in that green box, big G, big M, small m over r. So really, this question could have even probed us even more and made us prove that total energy is really just negative 1/2 big G, big M, small m over r. Doesn't that look very similar to something we have already? This is what the rest of these questions are trying to get us to show. Given that this is total energy, E total, okay? Let's see, because this looks like kinetic energy, the potential energy. It's all base of big G, big M, small m over r. Well, let's see if we can show that here. So we know that kinetic energy is 1/2 mv squared, but kinetic energy is also this. This is kinetic energy. This other one over here, we already know this is potential energy, so there's no question to that. But kinetic energy now takes on a new form, and that is 1/2 big G, big M, small m over r. Total energy has this new thing that we showed or proved over here, which is negative 1/2 big G, big M, small m over r. So really, these two are exactly the same thing, and the only thing that E total has is this extra negative sign. And that's true, because E total is, if you take this kinetic energy and you put a negative of it in front of it. So if you put a negative here, okay, then I get negative 1/2 big G, big M, small m over r, just like E total. Same. After you put a negative sign, okay? Okay, so that is why they are related. Well, let's take a look at E total, the next one, B. I probably should write this a little bit better here, okay? But let's start off with EP, okay? EP is negative big G, big M, small m over r from your formula sheet, okay? And we have E total is negative 1/2 big G, exactly the same thing. Whoops, missing that here. Now, really, if I took 1/2 of EP, so if I multiply both sides by 1/2, then this side I get negative 1/2 big G big M small m over R, which is equal to the E total. They're all related. They're all kind of very similar. We can even do this one more time. I know you're kind of getting tired of it, but isn't that really cool how they're all related in this way? And you're probably asking, well, can I, is this on the formula sheet? Do I have to remember this on the test? Well, it's more important than that we are able to show this, right? Or we can do this ourselves. Maybe I'll put that on the test question. Make you prove this, that kind of thing. Okay, so last one, I have EP. I got that written down. EK, we already know this is a positive 1/2 big G, big M, small m over R. Now, to get EP to look like, actually no, the opposite. I need to get EK to look like EP. So I just have to multiply this by -2. If I multiply this by -2, like this, okay, then this 2 cancels out with the 1/2. Then I get negative big G, big M, small m over R, which is equal to potential energy. Wow, look at that. Isn't that beautiful? Look at this interesting relationship. So all of potential energy, kinetic energy, and total energy are all based off of this big G, big M, small m over R. So this video, I've proved how total energy looks very similar to potential energy, kinetic energy, and this is specifically of objects that are in orbit, okay? If they're not in orbit, kinetic energy does not take that form. Okay, so we just have to be careful there. What I'm going to do in the next video is I'm going to show us how to take all of these relationships and apply to calculating for total energy of objects that are in orbit. Well, hopefully you found this video useful, and so maybe you'll stay tuned to the next one where we apply this to problems. Fat Mama Physics, signing out.